Okay, so today we're going to be doing two examples of what's called divide and conquer, but similar to, or sort of, very similar in spirit to the merge sort algorithm we did in our first lecture, but two different fun problems. So, all right, so our first problem. Okay, so the input. All right, so our input is a set of n comparable numbers. Uh, uh, in some array A1 through n, they're not sorted. That's what makes a problem interesting. So I'm just giving you n comparable elements, they're not sorted, and I give you some index k, like 10 or 100 or n over 2. And I want the 10th smallest, n over 2 smallest element in the array. Okay, so an example would be finding the median. That would be n over 2 or rounded up to make sure it's an integer. So here, I guess I've given an example of 11 problems. 11 numbers. And the question is, what is the median of these 11 numbers? I actually don't know. What's the median of these 11 numbers? I heard 56. Anyone else feel like it's 56? Who thinks it's 56? Can I say that's like 20%? Any other nominations? Okay, I guess we can verify if something is the median a little more easily. So there's 11 numbers total, so there should be 5 numbers smaller than 56 and 5 numbers bigger. So on the smaller side, we have 10, 24, 36, 27, 50. So that's 5. Okay, so I think that is the median then. Okay, well, I hope this example shows that it's not even that easy of a problem. At least you have to stare at it for a while for just 11 numbers to figure out which is the median, at least for me. All right, so if you wanted to solve this problem, what's sort of the obvious approach? What's the first idea that comes to mind? Uh, Sorting, yeah, so the natural idea is to just sort these numbers first, and then look up the k's smallest number, right? That'll take you n log n time. So, the only way the question is interesting is if we ask if we can do better than sorting the numbers, right? So is it really necessary to sort all n numbers to find a median or n over third or whatever element? Okay. All right, so the first step then is we're going to set up a recursive algorithm trying to do faster, but let's not worry too much about speed yet. Let's just do the obligatory sentence, okay, to set up our recursive algorithm. Does anyone want to suggest a specification for a selection algorithm? It's not sophisticated. Anyone? Similarly, you just have to identify what's the input and what's the output. Yeah, or comparable elements. Okay, I think goes smallest. Okay, and the only other thing we're missing is some kind of name to make our parameters clear, right? So let's call this select, taking as input A and K. Okay, all right, now we're kind of set, we're ready to go. Maybe we can come back and revise the sentence if we find it necessary. Okay, All right. I guess that's basically what I wrote. No big deal. All right, let's get to the fun part. Trying to implement this thing fast. All right. So, well, of course, there's going to end up being a trick and a way to do this very fast, but once I tell you guys, you won't get a chance to think about this again. So I thought I would first just try to get any interesting ideas out of you guys. Our goal is to implement select as described in a recursive specification. We want the overall algorithm to be even faster than sorting. Okay. Anyone have any ideas for how to implement this? I'm kind of curious to see what you guys might come up with if you haven't seen this before. Yeah. Okay, so yeah, if n equals 0, we should abort or make a lot of noise. If n equals 1, it should be k equals 1, you return the element. Okay, so base cases are kind of okay. Fine. Okay, that's the easy part. But how about now some real algorithmic ideas? Again, I don't really expect people to necessarily guess the ultimate idea unless they've seen this before, but it's kind of fun to try if you haven't. Yeah. It's easy to what? So I can verify if something is the median. That's true. Not clear how to use that fact. Um, okay, so I do know how to. I can verify. Okay, so it's worth pointing out that we can verify something in linear time, right? So if out of A, you told me, oh, this number is the k smallest, then I just have to compare that element to everyone else, and then that'll only take linear time. So it is true that we can verify linear time, which gives us some hope that maybe we can find it in linear time as well. That's always good to kind of think about. Okay, well, as a hint, then we are going to try to do some kind of quote unquote divide and conquer approach. Yeah. Okay, so if our goal is to find the smallest, for example, like you said, so if k was 1, that problem's actually quite easy. You could do a tournament and they annihilate each other, or you could just scan and find the smallest one as well. Okay, smallest is actually not so bad. The hard cases are probably closer to things like the median and stuff. It was like if it was the second smallest, third smallest, that would also be kind of easy. Any constant extreme, biggest, second biggest, that would also be easy. Yeah, tournament's not. It's sort of an interesting idea for some other problems that would work. Um, Here, like for the median or something, those pairwise comparisons aren't going to. Well, it's hard to see how that factors into finding out what's in the middle because it's not clear. Like if you're the bigger one of a pair, does that mean you're closer to median or further? Like it's not clear if winning or losing helps. Yeah. Okay, so let me just try my best to regurgitate. So you want to start with like two empty piles. Is that what you're saying? Okay, so and one was supposed to be increasing, one was supposed to be decreasing or something, right? Okay, so I'm going through the elements one by one. What do I do with the first element? In a descending order heap, okay. So what do I do on the second element? It's kind of complicated, yeah. what qualifies for being in there? Because you're saying I have some like two heaps, some increasing heap, decreasing heap, or something. And you think I should put x1 in the decreasing heap. It goes on top probably.
Yeah, so the decreasing heap basically has all the elements below median, and the increasing heap has all the elements greater than the median.
Okay, so certainly, well, let's say you're trying to find a median. Yeah, okay, I agree that if you can somehow make two piles where everything's bigger or smaller than a median, you'll be able to find a median. But to make the piles, it seems like you need the median.
Yeah, so first you add to the decreasing heap, and then for each element you just compare it with the top one in the decreasing heap, and if it's more than that, you add the increasing heap.
Okay, so if it was like in reverse order, I'll just end up adding everything here or something. Okay, some kind of heap thing. But in general, also heaps kind of take log n time per operation. So if you're kind of processing everything through a heap, you might still end up with n log n one way or another. Okay, yeah. Or okay, so sorting, yeah, but that takes n log n. I want to do better than n log n. Okay, so let's go back to a question. Just a conceptual question. It's sort of cheating, doesn't make sense, but what are some natural ways to try to divide the input into roughly halves to find the k smallest? Yeah,
Irrespective of the order,
yeah.
you could simply just do a division to get two different sets and then keep dividing until you get binary sets.
Sure. Okay, then what do you do when you're down to the bottom? You're saying I have a bunch of elements, I split them in half, and I split that in half, right?
Yep.
Uh-huh.
So potentially you might probably have to do some sorting, maybe at the lowest level,
Uh-huh.
but that's as far as mine can go.
Okay. Well, I'll say one thing that sometimes people suggest is let's split the input in half just as given. So it's not sorted or anything, so there's not much meaning to the halves. And then I don't know, I'll compute like a median over here, or I'll compute the kth biggest over here and compute the kth biggest over here and try to combine it. I'll find the k smallest on each side and try to combine it or something. But it's not clear how to combine the solution, or you could do k over 2 on each side and that. It doesn't quite. Okay, so okay, this is just for fun anyway. Um, okay, rats, I made a mess of this. Set link. Okay, so suppose, uh, okay, let's cheat a little bit. So, okay, in general, I want to find the k smallest, right? That's a more general problem. And suppose, just for a thought experiment, we'll figure out how to address this later. But just as an experiment, I told you that you had access to a linear time subroutine for median. So median's a special case, so it doesn't necessarily imply you can solve the kth, right? Even though kth would give you median. This is just a thought experiment. So let's say that you can do the median in linear time. Okay. How about now? How might you use this trick that I'm giving you for free to try to come up with a good algorithm to find the k smallest? Okay, so we can try to use the median to divide the input, right? This is kind of a different way to divide the input in two halves. Okay, sometimes this is called a pivot. So, all right, let's say that you can find the median, here's like some big array of elements and it's just some random point, right? But you can find the median and you can compare everyone to the median and then divide the input into two halves, right? Some numbers that are smaller, some numbers are bigger. They're not sorted on either side. They're just smaller and bigger, and you split the input in half, right? Okay, and that's great. So now what would you do after this? I know you said it out loud, but to say it again. Yeah, so if k is smaller than like n over 2 or so, you should go on the left and look in there. If k is bigger, then you should go on the right. And the nice thing is that you've half the search space in linear time, right? So, we just recurse on the appropriate half, which would, we don't have to think about it, but it would be dividing things in half even further, right? But we're just going to recurse, yeah.
I have a question.
Mm-hmm.
So that doesn't necessarily mean that the half that we're searching in has is ordered.
That's right. That's right. So, but if you look at the right problem, it's the same problem again, right? I have an unsorted array of elements, and I want to find a certain index. Now, we do have to remember that like k becomes k minus n over 2 on the right-hand side, right? Because you already got rid of k, or you've already got rid of n over 2 of the elements. So you have to update your index, right? But yeah, so it's totally fine it's unsorted, because that was our input coming in, and right, perfect. Okay, so, I guess if you want to implement it, this is not much, I don't know if this is very helpful, but that's what some code might look like, right? I get the median, and then I build out the two arrays, and depending on which side I want to go to, I'll recurse on that subproblem. Okay, this code probably looks more complicated than it is. All right, okay. Now, again, just setting aside the fact that we don't know how to compute the median, we're still cheating. What would the running time of this algorithm be? Okay, so let's first just write a formula for it. So I've got to start it with T of n is equal to, so how would I formulate this? Tn is equal to Tn over 2, because I'm going to do a subproblem of half the size, plus n plus big O of n, right? So n time to find the median, and then I recurse on the half, okay? So here, a recursion tree might be even overkill, but the first problem has size n, and then you just have one child, subproblem of size n over 2, one child, subproblem of size n over 4, and so forth, all the way down to a problem of size 1, okay? And the work we're doing is linear at each step, so I do n work on the first, n over 2 on the second, n over 4, the last level will do like 1, okay? If I add up all the work over all the subproblems, what's the total running time of my algorithm? Yeah, 2n. What's a 2 between friends? Yeah, right? So it's a geometrically decreasing sequence, right? 1/2 plus 1/4 plus 1/8 plus 1/16, it all adds up to 1. But in general, any constant less than 1, if it was like 2/3 plus 2/3 squared plus 2/3 cubed, it always adds up to a constant. 5/6, 5/6 squared, 5/6 cubed. Okay, it's always just a constant. The closer that number is to 1, the constant gets a little bigger, but again, what's a constant between friends? Okay, so if we had a linear time algorithm for median, we actually have a linear time algorithm for selection. Okay, so median actually is quite strong. We at some level have reduced selection to median. All right, so the obvious problem is that we don't have a linear time algorithm for median. If we had selection, we would have median, but okay. All right, so as a next thought experiment, suppose you had a linear time subroutine for like an approximate median. Okay, so this is going to relax it a little bit. It's not as strong as computing the exact median. So what the subroutine will do is it'll guarantees to return something like in the middle 80 percentile. So it'll return something with rank. So the rank of an element is like, if it's the median, it's rank n over 2. If it's the smallest, it's rank 1. If it's the biggest, it's rank n. It's ranking if you had ordered it. Let's say you have a subroutine called approximate median that returns some element with rank between like n over 10 and 9n over 10. I kind of chose those fractions arbitrarily, but the point is it'll be from the middle 80% and not from the two extreme 10%. Okay. All right. What might you do with this algorithm, or how might you make an algorithm with this subroutine?
You can just do binary again and send the lesser one to the left, higher one
Okay, so we can still follow the same approach and see how it does, right? All right, so you're given some unsort set of elements, you compute the approximate median, and then you can split into two piles. Now the piles might be somewhat uneven, right? So here now we have more elements bigger than smaller, okay? And then whatever, based on compared to last time, you actually don't know the rank of the approximate median until you calculate it, right? So you do need to compare, your approximate median with everyone and figure out, oh, the rank is like n over 3 or n over 4. It's not necessarily n over 2. You compare k with the rank, figure out which half you need to go into, okay, and recurse. Okay, and you recurse on the appropriate half. In the bad case, you'll be stuck going to the bigger half. Okay. All right, you have to update your index. K might change, right, because you've thrown away some elements. Okay. All right. So then here might be the implementation with approximate median. The only difference, from what I can tell, is that you do need to spend some time comparing P to every element to identify its rank L, and decide, oh, if K is bigger than L, I go on this side. If K is smaller than L, I go on the other side. Okay, that's the only difference, but that's kind of obvious. All right. So now let's try to figure out the running time of this, right? So the what troubles us is that I'm not necessarily dividing the input in half. So before it was kind of easy to see, I'm getting rid of half, getting rid of half, getting rid of half. It was all going to add to 2 line or something, right? But now I might not, right? Because it's kind of unbalanced. So let's see how that works out. So first I need to model this. All right, so Tn is equal to what? And think of the worst case. Yeah, I heard it, but not clearly. Someone say clearly. Don't be shy.
So 9
Okay.
times n over.
Okay, so in the worst case, we'll go to the big half, which will have like 9n over 10 elements, and plus what? Okay, plus n. Okay. All right. So that's like the worst case. I get rid of only 10% of the elements, and I'm still stuck with 90%, right? All right. So how does that work out to? Okay, we'll start doing the same thing. N. First problem has size n. Next problem will have size 9n over 10. The next problem will have size, 9 over 10 squared times n, all the way down to 1. So this will probably be a longer chain than last time because we're not throwing away as many elements. All right, how much work do I do at each level, right? Top level, I do about n work. Next level, I do 9n over 10. Next level, I do 9 over 10 squared, right? In general, at the ith level, I'll be doing 9 over 10 to the I times n, okay? What does this all add up to? Yeah, so this is going to be some sum. You can even let it go to infinity, and it's fine, right? So the n is always there, and then you have these 9 over 10s that are getting smaller and smaller and smaller, right? But it's a geometrically decreasing sequence, okay? This is a constant. It's probably like around 10, because it's like 1 minus 1 over 1 minus 1 minus 9 over 10. It doesn't matter too much. It's a constant. As soon as you get a number that's smaller than 1, 9/10, 99 over 100, 999 divided by 1,000, it's just a constant, geometrically decreasing sequence, and you're done. Don't think about it too much more than that, because you want to focus on the algorithmic stuff and the real ideas at play. Don't worry about, if you're getting the best constant. Okay. All right. So even with an unbalanced and approximate median, you're still going to get a linear time algorithm. So this is nice, right? Because approximate median is not, it could be potentially much easier than getting the exact median. The exact median seems awfully close to the original selection problem. But the approximate median, there's a lot of slack, right? Roughly 80% of the numbers are fine. You can even randomly guess and you'll be right most of the time. That's a different algorithm. All right, so, okay, so now all that remains is trying to figure out how to implement this approximate median in linear time. Then we're done. All right, so, actually, well, I guess I can always ask. Does anyone have any ideas, like crazy ideas? The ultimate solution is pretty creative, so it's quite hard to guess, yeah.
Can we use approximate median for select?
Well, yeah, so at some level, what we've shown is that if you have approximate median, then you have select in linear time. So we have used approximate median for select. Now, using select for approximate median is not very compelling because I think we all knew that select should be harder than approximate median. Not easy. So I don't know how anyone can guess this, but still, again, this is your only chance to try before I reveal the answer. Then you'll never forget. Yeah.
Divide all the elements into 10 groups.
Okay. So I'm going to kind of chunk it. This might not come out to 10, but yeah, I'm just trying to. Okay, so I can chunk it.
Maybe we can somehow pick the smallest or largest element in each group. After picking the, for example, smallest one in each group, we can compare that.
Okay, so I can maybe like look for it. So I know finding the smallest is easy, right? Maybe that's one thing you're leveraging. And I can maybe look at the smallest of each one.
And compare the 10 smallest elements
Uh,
and pick the largest one among the smallest ones.
okay, so you said first to divide it into 10 groups and find the smallest. But maybe if you divide it into groups of 10 and you get the smallest of each one. Okay, so in other words, out of n, suppose, okay, I'll make it a little bit smaller. Suppose each of these represented a group of 10 elements. And I get the smallest of each one. This is actually not a bad idea. Okay, so it's going to be, various points in these groups, but I can find the smallest pretty quickly. And then get the biggest out of the smallest. Then I know that element is at least bigger than n over 10 elements, right? But there is an issue though. Okay, so does the idea at least make sense? So I can divide it into groups of 10. So I have n over 10 groups of 10. Get the smallest from each group, right? And get the biggest of those smallest guys. That biggest of the smallest will be bigger than at least those roughly n over 10 other small ones. So it won't be one of the smallest. It'll be safe on that extreme, right? Okay. So that sounds good so far, but there is an issue with this argument. Anyone see? I so the biggest of the smallest could still be like the 10th biggest overall. If just in this last block just had the 10 biggest elements, the smallest of them would still be big overall. So focusing on the smallest is that's actually not such a bad idea though. It's quite close to what we'll end up doing. Oh, okay. So I divide it into 10 groups. So I'll put that. That's not exactly 10, but that's 8. I divide it into 8 groups, and then what? Okay, so I divide into 10 groups, and so what does it mean? What is the smallest one? Like one group may have some small numbers and some big numbers. Oh, n groups. Well, then, if you have n groups, then each one will just have one element. Oh, so you end up getting rid of the smallest and biggest element, and that'll get you to a problem of size n minus 2. So when we do divide and conquer, and when it works really well, we're chopping off like a constant fraction of the input. If we just get rid of like two elements, if we spend n time and we end up just getting rid of two elements, we'll basically have to do it n more times, right? And you'll get an n squared type of running time. So getting rid of just two elements is not strong enough. The rank what? The Well, we're not doing randomized algorithms. Uh, did you mean random? Did you mean random? No. Arbitrary? Okay, so a 2 over n fraction of the array. So that's just two elements. Sorry, I'm always bad with the by. One fifth fraction of the elements. So I want to make five groups. Okay, so look, here's 1, 2, 3, 4. Imagine those were actually evenly spaced out. Okay, so I've divided the input, I think, into five. Oh, that's six groups, isn't it? Okay, so here I've divided the array into five groups, and what should I do? I'll find a median of each. Find a median. Okay, let's say I find a median in this one. Oh, okay. Does that work? Okay, so just look at the middle. Okay. So in other words, let's just look at basically any arbitrary 20% of the array and then find the exact median inside. Okay. So the one thing tough is that now you need to find the median of something. Yeah, okay. So does that work? Okay. Okay. So at some level, like this could reduce to another select problem, right? So this is going to be some whatever the number is, and this is looking at your middle chunk. And so if you end up like plopping this back into here, right? So your approximate median is actually reducing to another call to select, right? With 20% of the elements. Okay. So if we had done that, and this running time will instead become, this is not a bad idea, but I think this is where it's going to have trouble. So now you have your running time, which is calling select on 1/5 of the array, plus, just like before, you have your 9n over 10 plus n. Okay, and so if you do the recursion tree here, okay, you have your problem of size n, right? And then you're going to get a problem of size n over 5 and a problem of size 9n over 10. Okay, and they're both doing linear work. So if you add this up, you're going to get whatever 11n over 10 total work. Okay, and if you went down another level, okay, you'll get like n of 1 over 5 times 9 over 10 and n times 1 over 5 squared and stuff like that. And if you actually add all this up, you'll get again 11 over 10 squared times n. So it'll actually be going up. You'll get a geometrically increasing sequence, which is bad news. So this will actually come out slower, but it's not a bad idea. Okay, yeah.
The basic idea is that if we have limit size of elements we have in the sorted and we get the mean. So if we can divide the chunks and recursively divide chunks into k chunks and find the median of the last leaf level subtotal and combine the median, sort them again, find the median and till the end. So the only problem is that our finding median may not be exact median, and we need to provide an approximation ratio of, can we give a guarantee of in what range should the median be always be. And if we can provide a range and by optimize the k chunks, we might be able to find the result that can give some guarantee.
Yeah, but so I mean, if you just keep dividing things down, you have to be careful that you're not. I kind of make. I'm not sure if it makes sense because you're still just kind of punting at the end of like where does the approximate. I mean, at the end we have to figure out how to do the approximation, and like we're still not. I mean, we still haven't addressed almost the hard part, right?
Yeah, because if you think about that, the median can give approximation of it cannot be too bad because each median base at least have other elements. So the median of median at least.
Oh, okay. All right, so let's just go. I think you're approaching the actual idea, which is also similar to another. Okay, so here's this median of medians trick. Okay, it's similar to the idea where we divided things into 10 and we tried to get the smallest, but it didn't quite work. Suppose instead you had divided things into groups of 10 and took the median of each of those groups of 10, right? Median in general, we don't know how to do, but I know how to get the median of 10 elements in constant time, right? Because 10 log 10 to sort it is constant time, okay? So that's what we're going to do. We're going to do 5 instead of 10. So we take A and we divide it into chunks of 5. I guess you could have done any number, bigger number, but 5 suffices. Okay, so divide it into groups of 5, and out of that group of 5, you compute the median of each one. Okay, so you have the median of all these little groups of 5. Okay, and then you take all of those, and now you have an input of size n over 5. Okay, so you took everything divided into groups of 5, and you took the little medians of those, and now you have a smaller input of size n over 5. Okay, and then you're going to take that, and then we're going to recursively compute the median of this n over 5 by using select. Okay, so we are going to, so for groups of 5, it's obviously very easy to find the median of a group of 5. Okay, and so we're going to leverage that to get sort of like a smaller subset of the data. Okay, B, and the critical thing is that B is much smaller than A, right? Because it's only n over 5. And then we're going to recursively call median or select to find the actual median of your group of n over 5. And you're hoping that the median of medians, while it might not be the actual median of the original thing, is an approximate median of the original thing. Okay. All right. Okay. So does the algorithm make sense? Yeah. You want to divide A into 20 parts. Okay. Find the minimum in each part. Okay, so if you find the minimum of each part, it could just give you the 20 smallest elements overall, right? So the median of the 20 smallest elements overall is just going to be the 10 smallest element overall. So the 10th elements overall is not in the bottom, is not in the middle 80%, right? Because you're looking at, there's a difference between n over 10 and 10. So your algorithm will get you, at worst, the 10th smallest element. But that's the extreme part of n. N is colossal, right? N is essentially unbounded. Okay, yeah.
So determining the size of how you group the set, does it make a difference if you choose odd numbered group size and even numbered group size?
Well, odd is always nice because then you don't have to worry about tiebreakers for median. So it just we get to choose whatever we want. We're making the algorithm. I think that any number bigger than 5 would have been fine for this argument, and 5 was like big enough. I think 3 is not good enough if you work through the math. We can look back in hindsight, and even is just like annoying because the median of the even numbers is annoying, and yeah, so. But it probably would be okay, just not as convenient. I think it's partly for convenience we choose 5. Yeah. Absolutely. So we want to show that this trick will return us an approximate median. If so, then we can plug it back into select, right? All we need is to implement an approximate median, then we get median. So, okay, let's first try to argue that this will return some pivot. I guess we're going to do better than 80%. We're going to try to argue that it's in the middle, I guess 60%. Okay, that the rank is between 3n over 10 and 7n over 10. Okay, so it's slightly better than what we had before. Okay, so let's first verify this, and we'll see if it's good enough to get us our overall running time to be better. Okay, so not all parts of the argument have been fleshed out yet. All right, so how do you prove this? You can do it kind of by a picture. So, all right, so what I've done is I've taken A, and I've kind of, okay, imagine that the columns are each of the groups of 5, okay? And imagine I've reordered the columns so that the columns are in sorted order, so that the median's in the middle, okay? And then now imagine I reordered the columns. This is just for the proof, not for the algorithm, right? This is just to do a proof by picture. Imagine I've reordered the columns to be sorted according to the medians, okay? So that the median should be in the middle of the green. Okay, so the columns are sorting those groups of 5, and then I've ordered the groups of 5 so that the medians are in increasing order. Okay, this is just for the proof. The algorithm doesn't have to do this. Okay, so now I want to argue that purple is bigger than a lot of elements and smaller than a lot of elements, and it's an approximate median, right? So in this picture, okay, so in this picture, what are all the elements that are definitely smaller than purple? Yeah? All the green elements to the left. These are all definitely smaller, okay? Anything else that's definitely smaller or less than equal to? Definitely smaller or distinct. And everything above what we just highlighted, right? Not just these two, but also these. Okay? So all of those elements are definitely smaller. Okay? Definitely bigger would be very similar, right? It would be all the elements on the right and beneath. Okay, those are all the elements that are definitely bigger. Okay, so how many elements are and there might be, it's possible that this guy is smaller and stuff like that, right? There may be others. Okay, but we're just, in the worst case, at least those are smaller. Okay, so at least how many are smaller? Okay, so I know that out of the n over 5 groups, right, like half of them are including the median and to the left, right? So times 1/2, okay? And out of each of those groups, the median or to the median to the left, sorry, from your point of view, 3/5 of them are smaller, right? The middle row plus everything above. So we put all that together, and you get, did I do this? Oh, sorry. From each one, you get 3 are definitely smaller, not 3/5. So you put all that together, there's 3n over 10 that are smaller, so the rank's at least 3n over 10. Yeah. So in the recursion, I'm going to actually call an exact, and we'll have to address this in the running time later. But given the n over 5 green elements, I'm going to call an exact median on those, not an approximate median. So I'm going to get a subset that's smaller, but I'm going to lose some information. But on that subset, I'll call for the exact median. So the approximate median is using exact median. So there's some kind of crossing of streams here that we will need to address. Okay. All right, so that's the proof by picture. All right. All right, so what would be sort of the running time of this subroutine? Okay. So if we continue to let T of n be the running time of select, because we're using select, to compute the exact median, okay, what would be the running time of approximate median, or this median of medians? Okay. So Tn over 5, because I'm calling select on n over 5 elements, plus the big O of n, just to do the groups of 5 and get the median of each. Okay. All right. Okay. So now we're going to look at this algorithm, right? It's basically the approximate median thing from before, but I've now dropped in median of medians, which is that trick we just did. Okay. All right. Okay. All right. Let's analyze the running time. Okay. Our algorithm is a little bit different than approximate median. Okay. I mean, the thing we did before. So we'll have to redo this first part. How would I model the running time for my select algorithm using median of medians? Well, first, how long did median of medians take? Do you remember? Say it loud so that we can go quickly. All right. Tn over 5 plus big O of n, right? And then we also have to account for the recursive call, because it's just an approximate median and we split the input and we do a recursive call, right? How big could that subproblem be? 7/10. It's a little bit better than before. Before I did 9/10, but now we got a slightly better bound of 7n over 10. Okay. All right, so that's a running time. Okay. All right, so when I start to fill out this tree, okay, subproblem here has size n over 5. That's not great handwriting. N over 5. This subproblem has 7n over 10. This will be 1 over 5 squared times n. This will be, 1 over 5 times 7 over 10 times n. This will also be 1 over 5 times 7 over 10 n. And this will be, I guess, 7 over 10 squared. Okay? And you imagine the next level is going to be similar. Okay? What's the amount of work at each level? How much work is at the first level? This is easy. How much work is at the second level? This is relatively easy. 9n over 10. And how about the next one? Sorry. Yeah, it's going to be 9 over 10 squared. And one nice way to see, so obviously this is a little bit funkier than usual, right? But you can look at it this way. It's kind of clear that what this is doing is it's taking 1/5 plus 7/10 squared times n, right? Because you have one set of 1/5, 7/10 from the earlier level, and each of those are breaking down into a 1/5 and 7/10. So it's really 1/5 over 7/10 squared cubed fourth, which is 9n over 10. Okay, but you can visualize it as 1/5 plus 7/10 squared cubed fourth. Okay. So you're getting a bunch of these 9 over 10, to the I, times some n, right? For all these various values of I. What does it all add up to? We've done this before. All adds up to a constant. We get a linear time algorithm. Okay, so 9/10, 9/10 squared, 9/10 cubed. Just because 9/10 is smaller than 1, boom, that's a constant. Okay. All right. Here's a very clever algorithm. Somehow the approximate median opened up some slack, and we could sort of implement that thing just barely fast enough. It was important that the 1/5 plus 7/10 was smaller than 1. We needed that to be able to pull off this running time. Okay. So I think if you had done something bigger than 1/5, like 1/7, it would have been even easier. Okay. All right, any questions? All right, we're going to have to go a little bit faster in the second part, and we'll skip the third part. All right, so much for selection. The next problem is called, I guess we're okay, we have 20 minutes. Minimum Euclidean distance or closest pair of points in the plane. Okay, so the plane being R2, so XY coordinates. Okay, and we're looking at Euclidean distance, right? So this is like that Pythagorean theorem kind of thing. Rats. Right, one side plus the other side, the square root of them, the squares added up, right? Euclidean distance. Okay, so fine. So here's like a bunch of purple points in the plane, and I want to find what are the two closest points. I'm not really sure what the two closest points are. Maybe it's like, maybe these two? Yeah, I don't know. Okay, and that's some distance delta or something, right? So I want to determine this distance delta or find this pair of points. Okay. Now, what's an obvious approach to this algorithm? Or obvious algorithm? Yeah.
For every pair of points, list their distance and then select.
Yeah, so the obvious thing is to compare every pair of points, and that'll take n squared time. I just do a little math, and I just keep track of the biggest one, right? So the question is, can you do better? Right? And at some level, can you do better than comparing all pairs? Right? Which might seem kind of intuitive. I mean, if you could just look at it, right? Which we don't know how to program, but if you were able to look at it, it's quite clear that, oh, I shouldn't be comparing like these two things at opposite ends, right? There's some geometry here, and there's some like, oh, some pairs are much better candidates than others. So intuitively, there's some hope that I don't have to compare every pair of points to determine the closest pair. Okay, but we have to figure out how to take advantage of this. All right. Okay, so as a warm-up, it's sort of silly, but we could consider it a one-dimensional case, right? That would be easier than 2 dimensions. Okay, or maybe the y-coordinate is 0 for everyone. All right, so what might you do for this? Yeah.
Sort from left to right and then just go through linearly and figure out the smallest distance.
Yeah, exactly. So we could just sort the numbers, because they're giving you two as numbers, not actually drawn on a line for you, right? So you have to sort them and put them on the line like I have. And then you just scan and take n log n. Okay? So that's an obvious idea. I'll only point out that it's like a little bit hard to generalize this to R2, to the plane, because how are you going to sort 2-dimensional numbers? I mean, you can only sort by 1 dimension at a time. So I still thought it would be sort of an awkward question, but can anyone think of a different way to do a kind of divide and conquer spirit? That's not this idea in particular, because this idea in particular seems to have trouble when we run into R2. But again, focusing on R1. Yeah. Okay, so divide this thing into half. Good. And how can I divide the point set into half? Yeah, you can get the smallest and the largest point. Oh, the mean. Well, if the point set was like really lopsided, okay, so let's say that there was some point that's like way off on one, for you, way off on one side, right? Then the mean is just going to basically only put that element on one side and everything else on the other, because it'll be so far off. Huh? We could take the median. So when you actually want to divide things in half, you're looking for the median, not the mean. Okay. All right, so another approach is we can split at the median, okay? I can compute the two halves separately, okay? And then when I come back, I just have to compare like the two closest points to that median line. I guess here it's a line, maybe it's even number of points or something, okay? So I can get the smallest distance among pairs within the two halves. And then when I'm worried about the cross pairs, I only have to look at the two closest points to the median, right? Because the other points I can ignore. So that's another approach. And if you wrote out the running time, you would get like, okay, I needed to compute the median. That took linear time. I had two subproblems of size n over 2, plus I needed some constant work to do the last pair, right? And this is the same recurrence as, sorry, there should be 2 times Tn over 2. That's the same recurrence as merge sort from day 1, so you'll get the same running time. So that'll give you n log n. So this is actually the idea that we're going to try to generalize. Yeah. We're not sorting here.
How do we know which are the two closest points?
Well, okay, so you can figure out the biggest point on the one side and the smallest point on the other side by just scanning. Yeah, good point. All right, I should have said that. All right, so here is what we're going to do. Okay, so it's still a little awkward to ask what's the median of two-dimensional objects. What we're going to do is just focus on one dimension. Okay, I mean, we're going to get the median of just the x-coordinate first. Okay, so step 1 is I'm going to kind of find the median x-coordinate and then split the input there. I'll still split it into two halves, even though the y's may be varying. Okay. Step 2, oh rats. Step 2, I'm going to recurse on each half, okay, and find the minimum distance within the halves. So in this picture, it might be within the halves, like maybe this is the smallest that doesn't cross the blue line, okay, within the two halves. Okay. Now, step 3 is where things are going to get a little bit interesting. Okay. What we're going to do is we're going to look at sort of this like vertical band of width delta. So I'm trying my best to. Okay, so let's say that this is like roughly delta. Okay, something like that. Okay. Right. So imagine this width is supposed to be delta, and this width is supposed to be delta, right? So I'm going to just look at like a slice of the data. Okay. And then what we're going to do, and we'll have to figure out how to do this quickly, I keep making that mistake, is that I'm only going to look at the pairs between those two green lines. Okay. And then find the minimum distance pair, especially among those crossing the blue. Okay. So that would be like, maybe this or something. that would be some delta 1, and I would compare my new delta with the previous delta and output the smaller of the two. Okay, so that's going to be the algorithm at a high level. Okay, I'm going to do the minimum distance on each side. That's going to and I'm going to focus on this narrow part based on that value of delta returned from the recursive subcalls. All right. Okay, so what are some, before unveiling more pseudocode, what are some high-level observations, right? Or why is this sort of intuitive? Okay, so maybe okay. So one thing that's kind of obvious, right, is that this is very narrow. Like it's really very, very narrow. And okay. So the algorithm is going to have to roughly compare a lot of pairs that are in this column, right? But I want to suggest that there won't be that many comparisons to make, or the points will have to be I can only draw a limited number of purple dots sort of in this picture, but why? Well, because delta is small, but in particular, delta is the minimum distance between any pair of points on one side, right? So if I was to look at the left side, any 2 points on the left of the blue, but inside the green, have to be at least delta apart, because that's what I found out in my recursive subcall. So I can only pack them in so much because they have to be at least delta far apart, and the whole width of that column is delta. Okay, and same was the other side. Okay, so finding this minimum distance, and I'm kind of looking in this distance of delta, and I know everything is delta far apart as well on one side or the other of the blue. So there's some kind of constrained volume argument kind of going on here, where you can only fit in so many points, at least in a fixed vertical segment. Okay, and so there we have some kind of tension, and so there's some idea that, okay, maybe I don't have to make all the comparisons inside because the points have to be somewhat spread apart, and there's this tension. There's something simpler going on in there. Okay, and we just have to now sort of formalize this and make this useful. Okay, but that's yeah.
What if I have two n plus 1 points, n are on the left line equidistant, n are on the right line, and one is on the middle, so that will be the median line. So I still have to come.
So yeah, that's true. So the space is limited by the projector, but these could be going really long, and there could still ultimately be a lot of points inside. We could have all n points, n over 2 here, n over 2 there. They're just stacked up because they're all really close to the median. But one thing nice is that, kind of looking here, this point obviously doesn't have to be compared to this point, the top and the bottom, right? And so there's some kind of locality here, right, where roughly a point here, this is what the algorithm's ultimately going to do. Maybe to be safe, I should check a few points that are nearby, like maybe the 10 points that are directly underneath and the 10 points that are directly up above. And then beyond that, I can ignore it because they're forced to be all delta. You can only pack in so many points that are nearby. So if I look at a particular band, I mean, if I cut another horizontal slab, right, then I'm limited to only a small number of points. And that's what we're going to take advantage of. There could still be a lot of points, but this way I can avoid all the comparisons. All right, so let's see. It's coming up. Okay, so this is what the algorithm is going to do. So that was all to build intuition. Okay, so let's go through this kind of slowly. Base case, n is equal to 1. I just return positive infinity, no big deal. 2 points, I'll just return the distance between the 2 points, no big deal. All right, otherwise we compute the median in O(n) time. I divide the input into 2 parts, things that are smaller, things that are bigger. I recurse. Okay, and so delta is the smaller of the 2 halves. Okay, and then now P3 is this band, right? This is all the points where the x-coordinate is within delta of the median x-coordinate. So that's that vertical band. Okay, and then here we have to prove this works. Okay, but suppose I was going through the coordinates from top to bottom. So P1, P2, P3, P4. So I've already, imagine they're already sorted by y coordinate. You can do that in the first step before the algorithm even starts. right? So you only have to do it once ever. And then you're going to go down vertically through this band. And what the algorithm is going to do is it's only going to compute pairs of, say, index I and j, where I and j are within 10 of each other. Okay, so this point may compare to like the first 10 elements below it, and afterwards it'll just ignore everything else. And we're going to try to argue that it doesn't need to look beyond 10. I think 10 is a conservative number. You could probably get it down to like 5 or 3 or something. Okay, but the point is that we're going to do a limited number of comparisons working through the span. You're not going to compare all n squared comparisons. This way you're only spending big O of n time there, not spending n squared time doing this limited number of comparisons. Okay, so this is this key part, that I'm only comparing the indices that are very close. Pseudocode makes sense because there's a lot of notation up there. Okay, yeah.
So after the step 5 where we get in the delta, which is minimum of the left and right region,
Yeah.
right? Instead of taking the band as delta and delta, can't we take it as delta by 2 and delta by 2? The band width is the delta.
Yeah, the bandwidth, I guess, is 2 delta, including the 2 sides. Sorry?
Yeah, instead of 2 delta, can we the full band width itself can it be a delta, like delta by 2 and delta by 2? Because then if there are points within those bands, then they'll be having distance that is minimum less than delta, right?
So if this was, okay, so let me zoom in. So if this was delta over 2 and it was delta over 2 on each side, right? A point that's like here and a point that's here could still be within delta, right? Because it's only leaping over delta over 2. But we would skip that comparison because it lies outside. Yeah, plus it's not a big deal. Like if I had done like 2 delta just to be safe or something, it won't change the running time much for a computer, only by constant. Yeah, but that's why we need delta is, yeah. Okay. Okay, good. All right, so, okay, what's the, all right, so let's look at this picture. Why doesn't this get bigger? Okay, so let's say that I'm looking at some point, say on the median, so A comma B, right? And okay, so a point, so this point here, okay, I'm only worried about points that are within distance delta, right? So I'm really only worried about comparing to any points that are like like it's not really drawn as a square, but that's sort of in this square here, if this was like a width delta, delta kind of thing, right? So anything below that square on that side will be at least distance delta away because the y coordinate has gone down by at least delta, okay? So what I want to argue now is that you can only pack in a small number of points. I said 10, and I think that's a massive overestimate, okay? That I can't actually fit that many points in that square, okay? Right. I think actually if you combine these two squares, yeah, there can only be so many points. Okay, and that's what I want to try to argue. Okay. So, okay. All right, so imagine it's something like this, right? So, what I want to do in the argument is count the number of points that lie in the square L. Okay, so L's dimensions are like this. Sorry, just getting a little crazy. Okay, but L is just that square of height and width delta with top right corner A comma B, where A was that median. Okay, and I want to argue that there can only be like a few points inside there. Okay, that seems intuitively clear because we know how to be delta apart, right? I just want to now get this down on paper and formalize it. So how can I argue that inside L there can only be a limited number of points?
There are infinite number of points. The border kind of more to the left should, there are infinite number of points inside the L.
Yeah, so okay, yeah, so how come there can only be like 3 or 4 points max? That's what I'm wondering. How come there can't be 11 points? How come there can't be 6 points? Yeah, okay, so they would have to be, and how can I kind of get that down on paper? Okay, so we can try to do what's called a geometric packing argument, and try to think about, okay, so, all right, so each of those, so every point that's inside here, right? I know they have to be delta apart from each other. Imagine drawing a ball around it of radius delta over 2, okay? Around any point that's inside this square. That's not really centered, but that's okay. Delta over 2, right? So if the centers are delta apart, then these balls have to be interior disjoint, right? So I can put a ball of radius delta over 2 centered at each point, and they have to be disjoint from each other. Okay? All right. Good. That's step 1. Now, how many balls can there be? Why is there a limit on the number of balls? Well, I should go quickly. I think we're going to run out of time. Okay. So what's the area of one of these balls, right? One of these balls is going to have area pi r squared or something, right? So that's pi times delta squared over 4. Okay, so they're all taking up pi delta squared over 4 units of space. And they're all sharing some common space. What's that common space? That entire ball, if I drew this square that's around it, okay, where I add an extra delta over 2, okay? So I take my original delta width ball, and I make it a 2 delta width, 2 delta width and height square, make it a 2 delta width and height square. All those balls have to be contained in it, right? Because the center is inside the middle, and it's only goes out by delta over 2. Okay? How much area is the outer square? The outer square has area 2 delta squared, right? So every ball is taking up area pi times delta squared over 4 out of a total of 4 delta squared. So I divide one by the other, divided by, pi delta squared over 4, and you're going to get like 16 over pi, and whatever, that's like 5 or something, right? Okay. So there can only be like 5 in one of those squares. Then you have 2 squares, one on each side, that gets you 10. That's why you only have to compare to 10. Okay, so this is called a geometric packing argument. It's pretty standard in geometric contexts. You can only pack so many balls. Yeah. Why do what? Sorry? Oh, no, so we recursively called find the minimum distance on each half, which will find the minimum distance, Euclidean distance, not just x-coordinate distance, including x and y. Yeah, I used the median x-coordinate to split them, but then now I know that on each side, all the points are at least delta far apart because I recursed on this side and said, oh, the minimum distance is delta, which could be diagonal distance, and stuff like that. So I know that everything has to be delta far apart. Okay. All right, so that explains why you only have to compare to 10 points going down from top to bottom, because there's only so many points that are going to be relevant because they're all kind of getting packed in there. And when we finally look at the running time, okay, Yeah, we're almost done. If I wanted to model the running time of this algorithm, so I start at t of n here, what would it be? Yeah, so what's the algorithm doing? It's going to recurse on 2 halves, right? So that's 2tn over 2, and how much additional work is it doing? Order n, right? Because you get the median, and then you just have to you go down this vertical band where each point gets compared to 10 other points. That's no big deal. All right, so you get 2tn over 2 plus big O of n. And what's that? What does that come out to? We've solved this before. Oh, rats. I always do this. N log n. Okay. All right, so that's how you get an n log n algorithm. That's obviously much better than comparing all pair points of points. Okay, so I don't know if there's any questions, but we're roughly running out of time. Any questions? Okay, so we'll have another couple of fun examples of divide and conquer next class. All right, thank you.